In the supersymmetric theory, the superpotential is given by the polynomial form of the superfield, especially the holomorphic superpotential is constructed by only the Kara superfield pi. There's no conjugate of the pi dagger. Such holomorphic superpotential is a complex analytic. The current example of the holomorphic superpotential is the Kara potential, which is the non-holomorphic, because this is also depends on the conjugates of the Kara superfield. The result of the holomorphy is the non-renormalization theorem. If we calculate the effective superpotential, it is the same with the three-level superpotential in the Wilsonian pictures. So there are no loop corrections during the upstem, where the Lagrangian contribution from the superpotential is given by the Grassmann integrations of the superpotentials. As a toy model, let's consider the Parsimino model as example. The superpotentials has mass dimensions of the three, so that we can construct sort of the superpotential W as the following form. We neglect the linear term because that only contributes the third pool. So the M has a mass dimensions and lambda is a massless coupling here. So this term includes the equal interactions. For example, this lambda cubic term in the component field level. There is the pi psi by pi interactions. And also we can introduce the one independent symmetry in the social algebra. This is called R charges. If we compute the commutative relations between the R charge and the supercharge, then it yields the supercharges Q. This means that if we ask the R for the specific component field, the R charges between the fermion component field and the scalar component field is the -1, and the R charges of the Grassmann number is equal to the 1. So if we consider the R charges of each component field, like as a Grassmann number that yield the R charges with the -2, and the superpotential W carries the R charges of the two because the Lagrangian is invariance under this R symmetry. And each component field, we can choose the R charges of the Kara superfields as a 1, and then the quadratic term has R charges of the 2, so that the mass coupling has 0 R charges. And the cubic term has R charges of the 3, so the massless coupling lambda has R charges of the -1. And the component field level, lambda has a -1 R charges, and the Lagrangian with the invariance and the R symmetry. So if we consider the following relation, the R charges of the pi and the psi has the difference is a -1, so we can find the R charges of the scalar component field. This is yield 1. And we can treat as the mass M and the coupling lambda as the some specific field which have the charge. This is called the Spurian technique in the quantum field theory. By using these Spurian techniques and imposing the R charges for each component field mass and the coupling, we can briefly derives the non-renormalization theorems of the holomorphic superpotential. Even in the loop effects that included, we can compute the effective superpotential. From the imposed symmetry, the possible and allowed effective superpotential is the following. First of all, we impose the R symmetry and the U1 symmetry and reasonable mass dimensions and the holomorphism for the superpotential. Then the effective superpotential, including all the quantum loop effect, should be the polynomial form of the lambda pi solved M. So lambda pi solved M has the zeros are charges, and it should be the polynomial form to satisfy the analysis arising from the holomorphy. So this is the only possible form of the effective potential. And for the extreme limit, especially the weak coupling lambda go to the 0, F zeros and G zeros reduces to the 1 for the smoothness. So the effective potential can be expanded in the power series form. So AN is a specific coefficient, and for the pi to the n to the plus, from here, for example, the first term, m pi squares lambda pi m and power. So if we compute this, so it's m to the 1 minus n and the lambda to the n and the pi to the n plus 2. So if we consider lambda go to the 0 limit, just the contributions from the other term, I mean the n larger than the 0, such a term does not contribute, and it is to the 1 only remain the n equal 0. Also for the function for the z, if we compute the same form, we can absorb such a term. So just effective potential has the following polynomial form. And for the last limit, when m goes to 0, also the f0 and the g0 should, I mean the m go to 0 and m go to 0, we want to reduce to the just 1. This means that this term m to the 1 minus n should be the m should not go to the denominator, so the n should be the smaller or equal to the 1. So the only possible term and the possible form of the effective superpotential is the same with the two level. So this proves the non-renormalizable theorems of the holomorphic superpotentials very simply. Also, we can include the kinetic term. In this case, there is a renormalization factors arising from the renormalized field. These factors are denoted by the z. And this kinetic term is actually the non-holomorphic because this is the function of the also for the conjugate of the coupling m daggers and the lambda dagger. Such a kinetic term of the component field pi and the spinor field psi arises from the d term pi dagger pi. This is not holomorphic superpotentials because there is a pi dagger dependent. So the such a coupling lambda and the mass m, the learning over the scale, like as learning coupling. Also, there are another proof based on the supergraph as a perturbative method. This also gives the same result of the non-renormalization theorem. There are no epithermal loop corrections in the superpotential. Also, we can construct the holomorphic coupling from the superfield strength because such a WI, such generalizations of the field strength of minus, and the Lagrangian contributions of the superfield strength also arising from the upstem. So that we can give the holomorphic coupling influence of such a superfield strength. And also we can consider the learning couplings for the such case coupling, and this gives us specific form of the beta function, so-called NSP beta function. Such a non-holomorphy I mean, the non-renormalization theorem to the holomorphic potential is applied to the subject already through constructing some advanced superpotential like ADR superpotentials from the supersymmetric study version.